Thank you very much for the kind introduction. I'm also extremely happy. This is the first time attending this conference because I'm a theoretician. Most time I didn't have chance to speak in this conference, so I really appreciate this opportunity. Thank Graham and Tao for the invitation. So I give a very big talk, but I'm only focused on a very small area. So this title is on the progress and the perspective of the single atom catalysis, but I will mainly doing two things. One is basic overview of this theoretical side of the single atom catalysis, and then also the extension of single atom catalysis to a few atoms. So that is what we call this single cluster catalysis, and then I will give a summary. So when we do call this name, many people are now starting to say single atom catalysis, but of course it's a very simple name. Sometimes people say it's too simple, that imply one atom. It's not a one atom. We are doing heterogeneous catalysis. It's always have a support with it. So we are all doing catalysis. So this is the diagram we use probably very often. So basically, as Thomas have said before, that if we don't do the active site of the atomic structure of the active site, we would not in the position to improve the existing catalysis or do a better one. So this is what we do. You change the chemical reaction paths basically to change the kinetics. Either you with heat or with electricity or with power, or with light, what you have done is just change the rate equation by adding a factor there. So that is all what we do. So then basically that is the active site, very important since the concept was proposed in 1925 by Taylor. So this concept has been well accepted in homogeneous and biological catalysis, because in that case, many times we kind of know where the reaction will occur, or sometimes difficult, but eventually we'll be able to identify them. But for heterogeneous, it's really a challenge. So that is because we are dealing with a huge system here. So that is the concept of this nanocatalysis world. So this field grew very quickly since Professor Hutchins and Haruta has developed this gold catalysis some decades ago. So then the heterogeneous side, the active side is not very well defined because we don't know where the reaction occurs. For example, we're dealing with usually the nanoparticles from the range of 4 nanometer to this 100 nanometers. So in other words, for a chemist, you're dealing with 2,000 atom to 30 million atom at the same time. So the reaction occurs somewhere, but we don't really know where it is. So because that, then many times we say, well, it's not atomically precise target for us because the nanoparticle usually have a range of distribution, have a huge number of atoms there, but it's not identical. So then in many cases, we only assume the reaction will occur on those kink or the different defect site. That is the problem for us to improve this catalysis. Heterogeneous catalysis always need a lot of experimental work to try and error because we have to find out which one's better and which condition. Then after many years' effort, we developed this from the bulk surface to nanoparticle, nanocluster, eventually to the very end to this limit, that is the single atom regime. While in 2011, Tao's group made this catalyst of the single atom platinum iron oxide. So then we discussed this extensively for over a few years, and then we eventually decided to call a name, because if one atom on a support surface can do chemistry like millions of atoms would do, then it would be a very good new catalyst. So we gave this name single atom catalyst. So since the name has been given, then this field grew also quickly. Well, I think the reason we call this a different name because if you look at this diagram, usually we think a single atom is not stable. But then if you consider because this atom itself is not stable, then they have to bind with something. That is the support, play a significant role in the single atom catalyst. So that is what we realized, that with the single atom supported on the support, basically they are binded to the support by some chemical interaction there. So then this can become a very stable system, eventually be able to do some catalysis. So this was the original concept of this single atom concept. So this paper was published in 2011, as many of you have known this. And after that, this field grew quickly, so they become one of the most cited papers in the Nature Chemistry journal. So among all the original papers, this is the very top cited one. So this is the symbol we suggested to use, because now we really know the active site, well, not necessarily being the active site, but it is a single atom supported on a support. The atom is well defined. So then we use this symbol to represent the single atom catalyst. And this field, as you probably seen, that it grew quickly. So in the past 10 years, there was a lot of paper in this area, and we had checked the Web of Science. In 2022, there was about 18,000 papers using this name. So that is the field we have done some research in different areas of them. Well, there are also, we hear many of different words about single atom related catalyst. For example, single atom catalyst, for us, what we think is this kind of a surface. You have a surface where some single atom supported or embedded on the surface. So it's well-defined active site. And then there are other concepts like atomically dispersed single atom. But the atomic dispersed metal catalyst is something meaning that the atom is singly dispersed, not necessarily a single atom. It could be a single atom or can be some cluster, so then they can coexist, for example. So this atomically dispersed would refer to a more broader category of this kind of catalyst. And there's also this famous single site heterogeneous catalyst. This is a very important concept, but they didn't define site. So site can be something one atom to 100 atoms, but as long as the site are the same, then they are single site heterogeneous catalyst. So we are limiting ourselves to the very narrow area here. So that is what we call, what is the single atom catalyst? So single atom catalyst we define as using this symbol here, and it represents a atomically precise heterogeneous catalyst. So that is the definition. You have an atomically precise heterogeneous catalyst, which has this substrate anchored stable and a reactive single atom active site. That is the feature. Because it have a very well-defined active center, so then eventually it have a high selectivity in many reactions. It turns out to be like that. So that is what we define using this name. Then with that definition, you can see actually it become more like a molecular problem. So you have a single atom supported on a support. The support atom surrounding the single atom form a ligand field. Then you can use in the quantum mechanical theory. So in quantum chemistry, if we're dealing with molecule, then you have an atom. For example, methane, you have a carbon atom surrounded by 4 hydrogen. You can use in this theory to define what is the atom. So then this is the quantum theory of atom. What is atom in molecules? So this method can be applied well to the solid states as well. So we can use this to characterize the single atom on the surface. Basically, now you have a quantum mechanical definition of what is a single atom, what is a charge, what is the bonding interaction with the neighbor. So that is the theoretical definition. So then this theory was originally applied to molecular problem by this theory of a beta. And then this can be now well applied to this single atom catalyst as well. So there's a paper published by one of my visitors. So they have done this kind of analysis of single atom catalyst. You have a lot of quantitative characterization of the single atom on surface. So that is a way we can now look at this thing with a quantum mechanical method. You can really define what is the feature of this single atom site. Well, single atom on an oxide surface, for example, actually could be very simple. If you look at the local structure, you have, if this is a metal oxide surface, you can see that when originally a metal atom is replaced by another metal, for example, on a iron oxide surface, if this metal is replaced by a platinum, now what you see is a single metal atom surrounded by a bunch of oxygen atoms. So for us, that almost looks like a ligand field of this oxygen surrounding this single atom. Of course, the chemical potential of the liquid of the support are different from the single or from complex because it's not a pure oxygen atom, but it's a part of the surface. So then you can view that locally as a chemically bonded single atom with the oxygen ligand with some extended surface environment there. So then you can do the quantum mechanical analysis of what is the difference between this single atom and a nanoparticle, for example. So what you can see here is that if you take an example of platinum atom versus the nanoparticle, you see the nanoparticle have a broader D band. And also the D band is high because usually the metal is in around the zero valent state. And then the oxide will also have some electron transfer to the support. So eventually you have this D band actually shift down. This is a very good feature if you considering CO oxidation reaction, then that means that CO binding with the single atom is weaker because now the platinum atom would be in high oxidation state than this nanoparticle, the single atom on the nanoparticles. So then this D band lower in energy compared with nanoparticle that offers some opportunity to tune this position, and then you can change the interaction between this single atom and the binding atom there. So this is what we summarized in the original paper there. So we said, well, single atom basically have a high atomic efficiency and also can have very high stability depending on the chemical bonding with the surface. And then they offer some of those features that partially vacant 5D orbital that can be used for catalysis and also have positive charge in the metal atom there because the charge transfer to the surface. More importantly, you change the oxidation state here because oxygen attracted some electron away, so then you have a covalent bond between metal and the oxygen atom there. So then this kind of feature make the single atom can be controlled using some chemical way. So if you look at this chemical bonding analysis, we see some interesting features. So we see strong metal support interaction, but that interaction is not defined in a chemical bonding concept. It's more a terminology, but in the chemical bonding side, you can look at the single atom now with chemical bonding analysis, you will see very interesting features. So first of all those metals are single metal are highly charged. For example, palladium here with positive 1.2. That means that metal actually has a high charge so that they can interact with the ligand via this electrostatic interaction, or in other words, it's an ionic bond between this ion and the oxygen atom there. But also, what is very important here, you have formed covalent bond between this metal atom and the oxygen ligand. We have analyzed a bond of different surface. We can see all those surface non-metallic element would have a covalent bond with a single atom supported. For example, here you see about 50% energy come from covalent bond. That is the reason why the single atom can be stable, because it's not just put there. They are binded with the surface with the chemical bond. So if you want to have the centering of the single atom, then you have to destroy the chemical bond first. In other words, change the oxidation state, destroy the chemical bond first. So this is why the single atom can be stable on the surface. Well, because of this feature, you can see now we have the single atom, we have a controller to manipulate the single atom. Previously, when we're dealing with a nanoparticle, then it's a huge nanoparticles on support. Even though you change the support, will change the catalytic property, but the effect is not that strong. Here, you have a direct control. What you have is, when you have this oxide changed, then the bonding change between the single atom and the surface. So they immediately change the chemical states of the single atom. So that will immediately affect the catalytic property. For example, we take this example here. If you put a gold single atom, that is Professor Hutchins' discovery in the 1980, right? So single atom gold on some environment. You can see here, if we put them on the oxide surface, with the titanium series, what you have is gold plus. So in other words, you have a positive charged gold atom here, but if you put the same gold atom on the zirconia hafnia surface, it becomes negative charged. Why is that? There is a quantum mechanical reason, because the chemical potential of the surface are different. You can see the 4f and 3d orbit is very contracted, so they can easily get reduced if you put an atom on it. So basically, it's a balance between the single atom and the surface chemical potential. And then if you have the single atom there, then they become a positive charge because this 4f and 3d is very contracted. But now if you put on the other oxide, then they are not easy to get reduced. So then you make this single atom negative charge. That gives us examples of we can basically adjust to this single atom surrounding environment, basically the local coordination number, also this environment of the distance, this kind of factor, or by changing the support itself, then you can control the catalytic property of the single atom. So then we established a chemical potential theory to explain the stability and the reactivity here. So this is basically the free energy of your system. You have the temperature, pressure, and the external field. Whatever it is, it can be electrical or light or anything. You can be belong to this one. And then this is the chemical species. So the free energy, then you look at the chemical potential defined this way, we will be able to calculate the single atom's chemical potential at different sites. For example, on this step position, the chemical potential is lower, and then the singly supported atom have a higher chemical potential. That is not very stable, but this one is very stable because the support defect actually bind this single atom well. And this is a nanoparticle, so you can look at here. The nanoparticle chemical potential is higher than the step position. So using this kind of tool, you can now analyze single atom versus nanoparticle. Then we can predict where the single atom will be stable, how to make them more stable, or how to see they might get centering with each other. So basically, you look at this diagram, we have found the linear relationship between the supporter, the probability of the supporter and the single atom. You can see that the reducibility of the support changes the charge state, as we see earlier. So when you gold put on oxide surface, you can make a positive charge gold or negative charge gold. So they will have different chemistry there. And also the linear, the relationship between the surface oxygen vacancy and this formation energy. So you can see basically we can predict on the surface where the single atom will have a high stability. So this is the diagram shows here. So we can do this kind of a screening of different system to find the better, highly stable system there. Using this theory, you can see where the single atom can be stable when it is not. So usually if you have a perfect surface, then the single atom on the surface will be easily get to this nanoparticle because the barrier to change to a nanoparticle is very low, and the nanoparticle have a stable state, so the chemical potential or the free energy favor this nanoparticle here. So that's why we usually don't have a stable single atom if you have a perfect surface there. And then many times we have a defect surface. If you have a defect surface, we already shown earlier, they have a better bonding with the surface. So the chemical potential is favoring the single atom compared with the nanoparticle. So they both can coexist. So that means in many nanoparticle catalysis system, you have both single atom and this nanoparticle coexisting there. It's only because we couldn't see them before. Now with more characterization tools, it might be possible to see those single atom in the nanoparticle system there. Well, if you have a surface, have some defect, which can embed this single atom, binding them very strongly, you actually can make them more stable than the nanoparticle. There are many experimental evidence now, so many single atom system can survive very high temperature, more than 1,000 degrees C because of this. So your surface binding with a single atom is so strong that will prevent them go back to the nanoparticle. Well, that is also one of the very distinguished paper by our chair, Professor Abaya. They found that when you have this nanoparticle heated, then eventually becomes single atom, and you cannot go back. So that is a very good way to make the single atom. So this is the chemical potential theory. We can explain when the single atom will be stable, how to make them stable. So then this diagram just explains what controls this stability there. Now, if that is the case, then we can converge all the concept of this single atom catalyst back to quantum mechanics, because the free energy, depending on this local part and the long-range part, if you look at the environment, whatever it is a surface or it is a ligand field of the complex, so you have a long-range interaction, but then the local part is actually you have ionic bond, a covalent bond, and a poly-repulsion. So that is a major chemical bonding factor that we'll be able to use to analyze this kind of system. We took this as a simple example, but if you have a single atom supported on a non-metallic surface, then you will be able to take advantage of this kind of analysis. So then, using the familiar molecular orbital theory, so we can analyze what is the interaction between the single atom and the environment here. So basically, when you have an ionic interaction via the Coulomb interaction, and then you have this covalent bonding interaction, that is the single atom have orbital overlap with the surface atom there. So then you can calculate the interaction integral here, and also the energy difference between the single atom and your surface atom. Then we'll define how stable this atom will be. And of course, there are some lone pair electron or some paired electron, they will be repulsive to each other. That is this poly-repulsion. In any case, so this is the local part of the strong interaction. You can use this kind of a theory to understand, to calculate, and then analyze the single atom interaction with the surface. And you can also use this to understand the reactivity, because if you look at this diagram, if we put a single atom inside a surrounding of a single atom environment, what you have done is you have this ligand part from the support become the bonding orbital. You have the d orbital partly become anti-bonding because they overlap with the ligand orbital. So eventually they have defined this delta E3 and E2 is the separation between the bonding and the anti-bonding orbital, which defines how stable the single atom would be. You can calculate that interaction. And then you have some states here, which are what we call catalytic quantum states, because those orbitals are not occupied and not interacting with the ligand from the support. So eventually, this is where the states will be responsible for interacting with the small molecule for catalysis. So that is why we say this part of the interaction, well, you can use the charge transfer to shift this d band up and down, but also this orbital interaction between these quantum states of the what do we call catalytic quantum states with the little molecules absorbed will be very important for the understanding of the catalytic procedure. So then you look at the single atom more like a molecular interaction here. So basically, if you have a single atom come to a surface, for example, CO molecule come to a single atom, then you can understand the interaction between that is the energy difference of single atom and the coming molecule, and then the integral here is the interaction overlap between the two orbitals. So we can use the quantum mechanics to calculate this kind of quantity to justify what is the interaction, how to make the system stable. So basically, there are two factors. One is the orbital energy difference here, and then the other is the overlap of the wave function. So that is, we can use this kind of procedure to screen catalyst. For example, if we took this single atom support on iron oxide, that is the first system Tao's group has made in 2011. So if we look at all the transition metals supported on that surface, you can see for a given reaction, what is the best single atom catalyst. So here we find this nickel, palladium, and platinum are the best system. So I think this provides an opportunity for computational chemists to predict catalyst before the experiment can be done. So this is the first part. I quickly introduce the area with some of the examples we have, the papers we have published. Well, so I will then introduce a little bit of extension of this, because single atom is very good is to have a well-defined active site That is the feature, and also because single atom bind with the surface via some of those covalent bonds, so you can adjust the chemical states of the single atom via the ligand, basically the support atom there. But it's a single atom. Sometimes the reaction might need more than one atom. Then we can extend this by taking advantage of single atom catalysts, but make them more complex. That is what we call single cluster. So basically the idea would be you have a nanoparticle, you split them into some single clusters supported on surface. It looks like a single atom except that they have a few atoms. It's a cluster. So why we do this? Because the nature has this for complicated procedure. For example, for the water oxidation, one manganese metal would not be enough because you need to change the oxidation state 4 times. One atom is not able to do that. Similarly, for this nitrogenase, right? So the female core would have 7 iron atoms to work together because they have a huge oxidation reaction here. You have changed a lot of steps to change the oxidation state. One atom would not be able to change so many times to be stable. So that's why they need a few atoms to work together using a cluster. That's the concept. So we basically using this bimetallic single cluster deposited on this surface, and then you can see if they can do some highly selective reaction like a single atom. So basically using the concept of single atom, but make them a few atoms, so like 2 to 4. Well, sometimes it looks like complicated if you make a single cluster, but it turns out on an oxide surface, if you put a single atom on this oxygen position, if you have an oxygen defect, then you put an extra single metal atom here, you can see the metal atom actually connected with a few other metal atoms of the surface. So basically that is a local metal cluster here already. This has been verified experimentally. So basically what you can see is the rhodium atom is surrounded by some cobalt. Of course, there might be oxygen from the support as well. So then with such an active site, you can do this kind of reaction, NO plus CO. So why we interested in this kind of bimetallic cluster is because the NO molecule prefer rhodium and the CO molecule prefer cobalt. So originally we thought, well, if we have 2 metals, one prefer A, one prefer B, then A and B must react with each other. So that is the concept. And then here you see we have 100% selectivity to form reaction. Because both molecules has got activated simultaneously, they have to react with each other to form a compound. So that is the product. So this is the first experimental theoretical collaboration. Then we verify this concept works. So then later we thought, okay, well, how can we learn from the nature? The nature has converted nitrogen to ammonia using a single cluster, which is the female core, the nitrogenase female core. But industrially, what we have done is using this very high energy procedure, using the dissociative mechanism to directly break down the nitrogen-nitrogen bond. That is the Haber-Bosch procedure for ammonia production. And the nature basically using a very simple, mild condition that is the associative mechanism. So basically add a proton and electron simultaneously, gradually you break a triple bond to a single bond and break. So then we thought, if we can make use of the single cluster, can we do something like this? You learn from the nature. Well, so basically we need to do is to break down this linear restriction of this BEP relationship, because that is why industrially you have to use a high pressure and this high temperature for the nitrogen to ammonia conversion. So then we are trying to construct some of this local cluster to learn this kind of feature. What we have done is actually the first cluster turns out we can use the rhodium cobalt one, which we just did the experiment with, that is NO plus CO reaction. And now we use this same class. We have theoretically verified that on this system, nitrogen can be converted to ammonia in a very mild condition using using the using the normal pressure, but only like 70 degrees C, we will already be able to convert nitrogen to ammonia on this ion, the rhodium cobalt cluster. We also tested on this ion cluster supported on alumina. So you can see on this alumina, they can also convert this ammonia, the nitrogen to ammonia, and a very mild condition. So that just indicating that, and this single class supported on oxide surface, it's possible that making use of this low oxidation state of the metal cluster to convert nitrogen to ammonia. Even though this is a pure theoretical work, but I hope that that will probably provide some insight. We can design this kind of system for future work to get this kind of conversion and a certain condition. The reason this can work is because we break this BEP relationship. You can see that the N2 dissociation and the NH dissociation are on different lines. So basically that means they are not restricted by the same BEP relationship anymore. This kind of proposal has been verified later by experiment. So basically on this work, in this work, the experimentalists find that the rhodium supported on some oxide surface. In this kind of condition, the nitrogen speed up the reaction. So usually we think when you add nitrogen as an inert gas, it will make the reaction slower. But here they make the reaction faster by adding nitrogen. What happened is exactly this reaction. So we have shown that on this kind of a cluster, then the nitrogen will be able to react with hydrogen to produce this NNH intermediate that will make this reaction fast. So that is provide some hint on how the nitrogen has been converted to ammonia. So basically, if you look at the procedure, what we said is the industrially, we directly break the NN bond. So that is you need a high pressure and high temperature there. But then the nature does in a very mild condition, the constant temperature and constant pressure, because they have this nitrogen, proton and electron gradually attached to nitrogen using this gradually, associatively have this nitrogen bond break. So then what we have done here is added the hydrogen atom on the single cluster gradually to this. So we're basically following this kind of procedure, but using the hydrogen atom rather than this proton. So then you can see why this kind of single cluster can achieve this normal condition conversion of nitrogen to ammonia. Well, with that concept, we thought, well, we need to look for some support that can stabilize the single atom. So the graphene die is one of the new material, carbon material. They have this natural hole there. So the hole is pretty big. If you look at the hole can support 3 atoms there. Okay, so I'm running out of time. I'll be to summarize quickly. So with this kind of a condition, you can see you have 3 metal atoms supported on this perfect hole here. Then you can make them very stable. So this is what we have looked at. This is 1 atom, 2 atom, 3 atom. You can see for 3D metals, all of them can be put them from 1 atom to 3 atom. This is the calculated binding energy there. This is for 4D metal, this is for 5D metal. So then we can screen all those metal atoms. How many atoms can be stabilized in the hole? It turns out 3 metal is very good to be stable there. You can see the bonding energy is very high here. So we use this single cluster to have done some HER calculation. We screened all the metal, find us a few metal would be good for HER, some is good for ORR, and another system would be good for this CO2RR. And then we can also find this kind of a cobalt 3 can do this CO plus NO environmental catalysis procedure. Okay, so I will skip that. Last example, I will show 2 slides. So this is a collaborative work with people in Singapore. Jun LI's group, they have made this kind of materials. It's a carbon nitrogen material which can support its 2 copper atom there. So the 2 carbon atoms separated as single atom in state. If you don't do catalysis, then this is a single atom. But then during the reaction, we find the 2 atoms will come together to bring 2 groups together, to couple them together. So this will provide a very good way to have a cross-coupling reaction, and then the chemical bonding of the copper actually help this procedure to occur. And that is my talk. I will summarize briefly. So basically what we have shown here is that you have a support which controls the chemical property of the product. So that is the support role. And then you have the reactant pressure, temperature, and the external field. So using this kind of well-defined single atom or single cluster active site, you will be able to control the product. It's like a mathematical function. Now you know from A to B the relationship between them. If you don't have a well-defined active site, you will not be able to control that. And then for the single atom, there are a few kinds of single atom. So this kind of is what we're looking for, static single atom. So basically, the single atom catalyst will respond to the reactant condition, but it doesn't destroy themselves during the reaction. That's what we call static catalytic system. But sometimes the single atom will move during the reaction, so they change the site. So we had a collaborative work with Philip Sautet and Philip Christopher on this topic as well. So the site will change during the reaction, but after reaction is returned to the single atom state. Sometimes you can see they will from single atom to cluster during the reaction, and there are some examples recently published, and we also find that there are some evidence the single atom can be generated from a single cluster or from nanoparticle during reaction. So that means some of the nanocatalyst is not a nanocatalyst. It is single atom catalyst because the single atom is dynamically generated during the reaction. So that is some of those examples. We also have experimental evidence to show this cluster to single atom transfer during the reaction. So that is a few different kinds of this system. Okay, so basically from single atom to single atom to two atom single cluster, all the way to single surface, you basically have a continuum Fermi level change. So depending on what kind of reaction you want to do, you can adjust this. Sometimes single atom is better, sometimes single cluster is better, sometimes surface is better. So that's why you can use this kind of a chemical bonding picture to understand the procedure. Okay, I will quickly show this one. This is the machine learning thing. So now machine learning become very powerful in computational chemistry. Now we can really use this to speed up the molecular dynamic simulation of single atom system because we have a well-defined active site. So we have recently done some work in that direction. And I will not summarize this, and I thank my collaborator, first Professor Tao Zhang. We had the first paper together on this, and we continue to collaborate in this field for the last decade. And also, those are the friends we collaborate in this area, and those are some of my students. Thank you very much for your attention.